Recording, great. So I tried to get the test marked, but like I said, I was feeling really sick yesterday, and so really better today, so that's good. But the tests aren't marked, so you'll have them back on Monday. Don't worry. As soon as they're marked, though, I'll put the marks on Moodle. You'll have them. When they're done, you'll know. Hopefully Moodle notifies you or something. I don't know how it works. So today we're gonna start part 3 I have here. Is it part 3? Yeah, part 3. So part 3 is on simple and compound interest. And I think chapter 4 is simple interest, I'm pretty sure. Chapter 4 is simple interest. And what we'll do today is 4.1, which is just the basics. Yeah. Say that again. Yeah. You won't be tested on linear programming and monopolies. So no derivatives on the final and no linear programming. Right? So that's done. You can forget about those. Okay. But yeah, there will be some stuff from chapter 1 or from the test 1. Okay, so 4.1 is called the basics. And just like in the other sections, we kind of cover this material and then we leave it for a little bit, but it's just good knowledge to have. And so I want to spend today just going through how do we deal with exponents and how do we deal with logarithms and why do we need them, why do we use them. And so that today will feel kind of a lot of theory heavy. So hang in there. So 4.1, the basics. I feel like every first section in the chapter is called the basics. Can't say for sure, but I don't know. It's always the basics. So we'll start with exponents. We've already dealt with some exponents. So exponents are just powers. For example, if you have something like a times a times a times a, and there's n a's, you can rewrite that as a to the power of n. Right? A squared would be a times a to the power of 3 is a times a. And so in general, we just write a to the power of n. So that's in general what an exponent looks like. And I'll just define some things here where a is the base and n is the power or exponent. So just to reiterate, a to the power of n is n a's multiplied together. So, for just a quick example, if you have 5 times 5 times 5 times 5 times 5, you have to rewrite that. You've got 1, 2, 3, 4, 5. So then you have 5 to the power of 5. Same idea. If you have to write out 2 to the power of 5, that's going to be 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5. Right. So far, so good. So what we're going to do now is we're going to write out the rules of exponents. These are on page 92 of your textbook. So I'm not making stuff up here. I'm just taking them from the textbook, and I'm just going to talk around them. Okay. And so the rules of exponents, which we'll have to know, and we've actually already used a couple of these, is on page 92. First, we're going to lay out some ground rules. Okay, we're going to let A be greater than 0, which is just to say that the base has to be a non-zero positive number. The base must be a non-zero positive number. That's one of the rules for all the rules that we're about to establish. And then we've got M and N have to be in the set of real numbers. And this is how you write it. So you do a little E like this, just says in the set. And then you've got a capital R with 2 lines as the ridge or the back. So it's just a capital R with 2 lines. And that's the set of real numbers. And so first I'll just write out what this is saying. So M and N are in the set of real numbers, is what that says. And the set of real numbers is any number between negative infinity and infinity. Okay, so all the numbers that we can think of are real numbers. Of course, you might know that there's imaginary numbers as well, right? The square root of -1 makes an imaginary number. We're not dealing with those. Okay, so the set of real numbers is any number between negative infinity and infinity. Okay. So now that we have those laid out, we can start writing down these rules that we'll be able to follow. So the first rule is the one that we've already talked about, and that is just to establish that A to the power of N is just A times A times A times A. And so I'll put the little my definition here in a lighter color, A multiplied N times. Okay. So that one's fine, right? Just A to the power of N is just A times A times A N times. N A's. Okay. The second rule that we've also sort of used already is that A to the power of M times A to the power of N, we can rewrite it as A to the power of M plus N. Okay. And so if you have the same base, you can combine them by adding up the exponents, okay, if they're being multiplied. So if multiplying powers of the same base we can simplify by adding the exponents. We can simplify by adding the exponents. So here we're multiplying the same base, right? If we're dividing the same base, we have this third rule. So if we have something like a to the power of m over a to the power of n, you can rewrite that as a to the power of m minus n. And so in words, if dividing powers of the same base, we can simplify by subtracting the exponents. We can simplify by subtracting the exponents. Oh. Fourth rule. If you have something like a to the power of m all to the power of n, you can rewrite that as a to the power of m times n. This is really just an extension of rule number 1, right? Because what you've got here is if you just treat a to the power of m as one thing, then a to the power of m to the power of n is just a to the power of m times a to the power of m times a to the power of m n times, right? And so what you get is just a to the power of m times n. And so I'll just say that this is an extension of rule number 1. That's this rule. And so that's just a fact. Similar idea, if you have something like a times b all to the power of m, as long as they're multiplying in there, you can bring the power inside. Multiplying or dividing, you can bring the power inside. That's not true if you're adding or subtracting inside the brackets. And I'll show you why in a sec. A to the power of m times b to the power of m. It's kind of the reverse of rule number no, not really. Never mind. It's because we have different bases. So if multiplying two bases the power expands inside onto both bases. If I had to guess, the next rule, it is just the same thing, but with division inside. So 6, if you have something like a over b all to the power of m, you can rewrite that as a to the power of m over b to the power of m, which is just an extension of rule number 5. Rule number 7, we've already talked about. A to the power of 0 is 1, right? We've already established that a few classes ago. So I'll just say that that's a fact. We don't have to explain it. Rule number 8, and we use this one quite a bit, is that a to the power of negative n is the same as 1 over a to the n. Okay. Which a lot of the time we work the other way, right? We have something 1 over a to the n, so then we rewrite it as a to the negative n, right? So if you're bringing a power from down in the denominator up, you just make the power negative, right? So we use that a lot, right? Just make the power negative and it's the same. So we can rewrite something in the denominator. Now I'm kind of explaining the other way around because that's how we use it most of the time. Something in the denominator. Remember, the denominator is the bottom of your fraction, right? Numerator, denominator. As something in the numerator with a negative power. I'll put in brackets here that we use this a lot. So that one's a good one to keep track of. Any questions so far? Just kind of going through the rules so we have them. Nine. A to the power of 1 over n is the same as the nth root of a. So the nth root, you put a square root, right? That's how we're used to reading them. But you can actually take any root and you just put it in the little hook here. Okay. So if you wanted to take the 3rd root, the 4th root, then you just put that number inside the hook, okay, of a. And to calculate it right on your calculator, you would just rewrite it as a to the power of 1 over 3 for the 3rd root, 1 over 4 for the 4th root, right? And you've probably used that trick maybe in high school when you had to take the 14th root or something like that, right? Use the 1 over in the power. So here, I'll just say we can rewrite the nth root as a power if needed. So whenever you have a root like that, you can, in your calculations, it'll be easier if you just convert the root to 1 over n as the power. Rule number 10 is just an extension of that. So a to the power of m over n. Now we know that we could rewrite this as a to the power of m to the power of 1 over n, right? And that's by rule number 4. But then this we can rewrite as the nth root of a to the power of m. Right, by rule number 9. So often we'll be working from this way, from the root to some power, right? But we should be flexible moving between the two, right? Depending on what we need. So those are all the exponent rules. Any questions before we do some examples? Kind of showing our way around here. Okay. Oh. Let's do example 117, which just says to simplify a to the power of 4 times a to the power of 8 over a to the power of 7. So we want this, right? We have one base, which is a, which means that we'll be able to condense this to just one a to the power of one number, right? And then it's simplified. So I'll start by writing it out here. A to the power of 4 times a to the power of 8 over a to the power of 7. And I'll just do my work over here. There's lots of ways that we could go about doing it, right? Because we're just multiplying and dividing. Is there a flicker? Or is that just me? Oh, there was a flicker, right? Okay. So we've got options. We could simplify the numerator first, right? Or we could bring up the a to the 7 to the top. Right? What I'm going to do is I'm going to simplify the numerator and then I'll bring up the a to the 7. But you could do it in kind of one swoop if you wanted to. But just to show what's going on, this becomes a to the power of 4 plus 8 over a to the power of 7. And here I'll just make a note by rule number 2, just to point you in the right direction. That's not something that I need you to do. You don't have to tell me which rule you're using. Just know them and use them. Okay. So this becomes a to the power of 12 over a to the power of 7. Okay. So now I can bring up this a to the power of 7 from the denominator to the numerator just by making that 7 negative, right? The power negative. So this becomes a to the power of 12 times a to the power of negative 7. By rule number 8. Was that 8? Yeah. So then, now again, we have 2 a's, so we can condense those by adding the powers. Right? So we have a to the power of 12 plus negative 7. This is by rule number 2. So this becomes a to the power of 5. Or solving another way, just to introduce you to a couple of ways, and then just pick the one that makes more sense to you, right? So always kind of do whatever comes easiest. So another way that we could simplify a to the power of 4 times a to the power of 8 over a to the power of 7, like I said, is just to bring up that a to the power of 7 right away. So then we have a to the power of 4 times a to the power of 8 times a to the power of -7. And that's by rule number 8. And then it doesn't matter actually how many of these bases you have. To smush them all together, you just add up all the powers, right? As long as they're the same base, which they are here, a, we get a to the power of 4 plus 8 plus -7 by rule number 2, which is a to the power of 5 again. All right, so it's just two ways that you could go about solving this problem. Both right. Okay. Any questions about that one? Okay. So let's do example 118, which is to simplify 1 plus I to the power of 3 times 1 plus I to the power of 9 all over 1 plus I to the power of 6. As long as you're looking at this and you're seeing 1 plus I as one thing, right? This has the same structure as the previous question, right? If you just pretend 1 plus I is a, then you have a to the power of 3 times a to the power of 9 over a to the power of 6, right? Here's where I'm going to throw in my warning shot about pulling in these powers. So before, right, we were pulling in those powers on a and b because they were either multiplying or dividing. And then I said, you can only do that if you're multiplying and dividing, right? So if we were to pull in this where we're adding or subtracting inside, right, I'm just going to show you that you don't get the same thing. Okay. So 1 plus I to the power of 3 does not equal 1 to the power of 3 plus I to the power of 3. Because, here, I'll just put warning above it. Warning. Warning, warning. Because I see this a lot where people try to pull in the powers and it just doesn't work. Because if we have 1 plus I to the power of 3, that is 1 plus I times 1 plus I times 1 plus I. We know that. Now we can expand these, right? And we can say, well, that's the same as, I like to do the first two and then expand into the third. So I get 1 plus 1 times 1 plus 1 times I plus I times 1 plus I squared times 1 plus I. Can simplify that just so we don't have to drag it all the way through. 1 plus 2I plus I squared times 1 plus I. Expand that again. So 1 times 1 is 1 plus I is I, or 1 times I. 2I times 1 is 2I plus 2I times I is 2I squared. Plus I squared times 1 is I squared plus I squared times I is I to the power of 3. Simplifying this, right? Collect like terms. We get 1 plus 3i plus 3i squared plus I to the power of 3. This is clearly not equal to 1 plus I to the power of 3. Right. So you have to be really careful if you catch yourself trying to do something like this, where you're just trying to pull in the powers on top of adding or subtracting in there, right? Just remember this mess, and you'll know you can't do it, right? So it only works, you can only pull in those powers if you're multiplying or dividing inside. I'll write that in a note here. We can only pull the power inside the brackets if we are multiplying or dividing inside not adding or subtracting. So that's really important. Otherwise, you'll have some illegal math. Yeah. So, well, first of all, if the question was to simplify this, your first thought might be to expand it, right? But we only did 1 plus I to the power of 3. Now imagine doing 1 plus I to the power of 9 times 1 plus I to the power of 3. That's a mess, right? So what you're going to do is you're just going to treat 1 plus I as one thing, right? A to the power of 3 times A to the power of 9, right? And so to simplify, we can treat 1 plus I as the base. And so if we have something like 1 plus I to the power of 3 times 1 plus I to the power of 9 over 1 plus I to the power of 6, we have the same base for all of these, right? And so these rules all apply, which is going to be 1 plus I to the power of 3 plus 9 over 1 plus I to the power of 6. If you wanted to, you could have moved the 1 plus I to the power of 6 up top already, right? Maybe that's what you like. By rule number 2, which becomes 1 plus I to the power of 12 times 1 plus I to the power of negative 6. Just doing two things at once here. By number 8. And then I can combine this 1 plus I to the power of 12 plus negative 6 by number 2, which makes 1 plus I to the power of 6. There are lots of ways that you could do this. As long as you get to 1 plus I to the power of 6, you probably did it right. Okay, so if you're not sure, if you're doing it a different way, then just show me and I can tell you if you're doing it legally. But you probably are, and you're probably fine. The point is that you're supposed to be able to handle these problems. No. You'll have to know these rules. On the plus side, we use just a few of them over and over again. So you'll know. How about another example? example 120. Oops. Simplify something like x plus 3 to the power of 5 all to the power of 3 over 2. Oh. So I'll just rewrite it over here. So we've got x plus 3 to the power of 5 to the power of 3 over 2. We said that if we've got a power and then a power on the outside, we can just multiply those together to combine them, right? And so we can rewrite this as x plus 3 to the power of 5 times 3 over 2 by rule number 4. But again, you don't have to tell me the rules that you're using, just use them. So this becomes x plus 3 to the power of 5 times 3 over 2 is 15 over 2. Treating x plus 3 as its own thing because we're adding inside, right? So we don't want to break this up. We've got 15 over 2, which means we have the square root, because that's in the denominator, right, of x plus 3 to the power of 15. Okay. So we've got the square root of x plus 3 to the power of 15. And this is by rule number 10. I'll throw in the 2 here just to show that it's there. But I'll just make a little note here that usually we write the square root as just the square root, right? But for any other root, we add the root number inside the hook. I don't know what the technical term of it is, but hopefully that makes sense. But for any other root, we add the, I'll put in quotes, root number in the hook of the root. In the hook of the root. For example, what I mean is x to the power of 1 over 3 is the third root, which is just x with a, well, the third root. I don't know how else to say it. Same idea, x to the power of 1 over 4 is the fourth root. Which is just the fourth root of x. So when do we use roots? We use roots to undo powers, right? And so if you have a power that you need to get rid of, just like if you've got an equation and you're subtracting a number on one side and you have to move it to the other side, right? You'd have to add it to both sides to get rid of it, to undo it. Okay. And so roots undo powers. So we use roots to, I'll say, undo powers. For example, if x to the power of 5, or in x to the power of 5, solve for x. So if we have x to the power of 5, let's say X to the power of 5 is 3. That'll make it a little bit easier to deal with. X to the power of 5 is 3, solve for x. It's easier when you don't have a floating value. So now, if you want to solve for x, you have to get rid of this fifth power, right? And so to do that, you're going to take the fifth root. Okay? So you're going to take the fifth root of x to the power of 5, but whatever you do to one side, you have to do to the other side, right? So you have to take the fifth root of 3. If we rewrite x to the power of 5 and then the square root of 5 as a power, right, you'll see why they go away. So you don't have to show this every time, but I just want to show you where it's coming from. So you've got x to the power of 5 to the power of 1 over 5, which is 3 to the power of 1 over 5. So then we can just expand those brackets, we can multiply those powers. So now we have x to the power of 5 times 1 over 5. 5 times 1 over 5 is just 1. So we've got x to the power of 1 is 3 to the power of 1 over 5. So now we've solved for x just by taking that fifth root. So we've got x is 3 to the power of 1 over 5. Any questions about that? How about example 121? Says solve xy squared is x squared minus y squared for y. We could have just as easily solved for x, but here we're going to solve for y. So we've got x times y squared is x squared minus y squared. Bless you. So we're going to solve for y, which means we have to move all the y's to one side and everything else to the other side. And so we'll start this migration here. And we'll say, okay, well, I'll move my y's to the left-hand side because I like to have whatever I'm solving for, I like to have on the left-hand side. Doesn't matter, but it's nice to have some rules. X times y squared plus y squared, right? Just moving the y squared over to the left-hand side. Here, I'll just make a note. Move y's to one side. I've got a common y squared that I can pull out, right? I can factor out a common y squared. So I've got y squared times x plus 1 is x squared. So here, I'm going to factor out the common y squared. So now I can divide both sides by x plus 1, right? Because I've got y on its own, and then I can just divide out the x plus 1. So now I've got y squared is x squared over x plus 1. Now I've solved for y squared, but I was supposed to solve for y, right? So now to solve for y, I have to take the square root of the y squared. So here, I'm going to say, take the square root of both sides to solve for y. So what I get is I get the y is the square root of x squared over x plus 1. One thing that I'll make a note of here is that it's actually plus or minus in front. Okay. So when we square things, all things that have been squared are all positive, right? It gets rid of the negative and it makes it all positive. So now when we take the square root to try to go back to the old numbers, we've lost that negative, right? And so we don't know if it's positive or negative, right? Or if it was positive or negative to begin with. And so that's why we have to put the plus minus in front if we've taken the square root. So here, I'll just make a note here. When we take the square root, we need to consider both positive and negative values of y. Both positive and negative values of y. And so to do that, you're going to add plus minus in front of the square root. In front of the square root. I would consider this simplified, right? But we could keep going if we wanted to, and just to play around with these rules, right? These exponent rules, we'll just keep simplifying it for a little bit. And so I would consider y is plus minus the square root of x to the power of 2 over x plus 1 simplified. But we could keep simplifying if we wanted to. And here's what it would look like. So you've got, y is plus minus the square root of x squared over x plus 1. We can rewrite that, right? We could rewrite the square root as everything to the power of 1 over 2. So we've got plus minus x squared over x plus 1 to the power of 1 over 2 by number 9. Now we can bring that power inside, right? Because we're multiplying and dividing, right? As long as we treat this x plus 1 as one number, we can bring the power inside. Okay. So then we get plus minus x squared times 1 over 2 all over x plus 1 to the 1 over 2 by number 6. So then we have plus minus x squared times, or x to the power of 2 times 1 over 2 is just x to the power of 1, which is just x. And then we can rewrite x plus 1 to the power of 1/2 as the square root of x plus 1 if we wanted to. I can't think of any way to simplify that even more. Now it's really, really simplified. Although I'd say it was simplified earlier too. Okay. So any questions about that? Oh. So we've been dealing with exponents. You've probably heard of exponential growth. So exponential growth is when it starts off slow and then all of a sudden it just starts building and building. It goes up and it increases really rapidly. Okay. And so in general, an exponential growth graph will look something like this. So you've got your X and your Y axes. And it'll start kind of looking like so, and then all of a sudden it just increases. And so it's slow, 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 and then all of a sudden, as soon as it starts picking up, it just shoots up. So that's exponential growth. Exponential, growth. Slow to start, but grows faster and faster with time. Grows faster and faster with time. So those are exponents. Another problem we could have is if we have x in the exponent, how are we going to solve for it? Right? And that's where logarithms come in. And so we know to solve for x in x to the power of 7, for example, we take the 7th root. We take the 7th root. Okay. What if we have to solve, oops. Seven to the power of x for x. We need logarithms. Logarithms. So if you've worked with logs before, you'll know that there's multiple bases. And so we're only going to use the natural log, which is log base e. So whenever I say log, that's the log that I mean. There's log base 10, which is pretty common, but for most sciences, you're going to use the natural logarithm. But let's just say here, so first, if we need to solve for a value in the exponent, need to solve for a value in the exponent, we will need to use logarithms. Which I'll just call logs from now on. So logs can have any base. And I'm just saying that in case you know something about logs. If you haven't used logs before, then don't worry about this next part. Okay. So logs can have any base. The most common bases are base 10 or base E. E is kind of like pi, right? It's a irrational number, never ends. And so E, which is approximately 2.71828, we will work exclusively, so only in log base E. Exclusively in log base E is how you write it. So you write log and then subscript E. Log base E. Also called the natural logarithm. Also called the natural logarithm. And denoted by ln. Sorry. But usually when I write it, it just ends up looking like that. I do this kind of handwritten blurb, ln. So as long as you're able to recognize that. If you're reading stuff and you don't know what it says, then just ask. So just like with exponents, we're going to develop some log laws. We're going to talk only in log base E, but of course all these rules apply to any base. Okay. And so all of the log laws we develop here apply to any base. Oops. Apply to any base. But we will only show the natural log. But we will only show the natural log ln. So here are the properties / rules of logs, or I like to call them log laws, just because it's way more fun to say. So again, we have to establish some rules, right, for these things to work. And so we are assuming that A and B are in the set of positive real numbers. So we can put a little positive here. And this is just saying that A and B must be positive, is all that's saying. In the set of real numbers. So so A and B can be any value from 0 to positive infinity. Can it include 0? Sort of, yes. First rule. The log of a to the power of b, we can rewrite, and this is really convenient, as b times the log of a. So you can see where this comes into play, right? If you want to solve for something that's up here, the only way to bring it down is by taking the log of it, right? So you'd have to take the log of both sides, right? But when you've taken the log, that means that you can bring down that power, and now it's down on a playing field that we can get to it at, right? And so that's going to be a big player for solving for things that are in the power, right? Just take the log of both sides, and then you can rewrite it like this. Second rule is very similar, right? The log of a to the negative b is negative b times the log of a. Here, I just want to make a note that recall that a to the power of negative b is actually 1 over a to the power of b. So what we've actually done is we've taken something like this, 1 over a to the power of b, rewritten it as a to the negative b before we plug it in here and take the log of it to bring the power out front. So what we were initially probably solving for was this b down here, right? So it works the same way. You just have to tweak it a little bit. How about 3? The log of a times b is the log of a plus the log of b, and vice versa, right? You've got the log of one thing plus the log of another thing. To combine those, you're going to multiply them inside the log. Same idea for the fourth rule. If you have the log, if you have the log of a over b, that's going to be the same as the log of a minus the log of b. So again, these are things that you have to memorize and know how to use, right? But I think what you'll find is you'll notice which formulas we use more than others, right? So as we use them, you'll notice which ones you need. Some of these you don't, like these 2, 3, and 4, they're not really, we don't use them a lot. You don't really need them. But they're just there for completeness. So, any questions about those rules? No? Keep going. Got it. How about an example? Let's start easy. So 4 is 3 to the power of x. Solve for x. So we want to solve for x. What we're going to do, or what we have to do, right, is take the log of both sides to bring that x down in front. So we're going to take the log of 4 is the log of 3 to the power of x. And then, so I'll just make a note here. Take log of both sides. And then we've got the log of 4. That's just the number, and I'll show you how to find it on your calculator. And then on the right-hand side, we can bring that x down in front. So now we have the log of 4 plus, or is equal to x times the log of 3. By rule number 1 of the logs. Now to solve for x, x is the log of 4 divided by the log of 3. To find the log of a number on your calculator, let me just see here. To find the log of 4 on your calculator, you're going to have 4 on your screen and then hit the ln button and then hit equals. And I get 1.386294,361. Okay, so whatever you have the log of that you want, you have to have that on your screen first, and then you can hit the ln button. And the ln button is just on the left-hand side, and it's capital L, capital N. So same idea, if we need the log of 3, can hit the 3 log. You don't need to hit the equals, but it's safer to just always hit the equals, because sometimes it'll show the answer right away and sometimes it doesn't. I don't know when it decides not to. So if you hit the equals, always it's safer. 1.09861228.9. Have I shown you guys how to store numbers? Yeah? Good. Because that's going to come in handy now. Right? What you can do, you can just have 4 on the screen, hit the ln, divided by 3 on the screen, hit the ln, equals. Right? But sometimes we'll have more numbers than that, and then you'll want to just store each value and put them in as you need them. But up here, what I'm going to have is x is going to be 1.261859507. Is that what you guys are getting to? Maybe? Yeah. So what I did here was I had 4 ln divided by 3 ln equals. Just trying to write out my calculator. Pardon? Oh, is it? Are you getting a different number? Same 1.2. Check in. And phew. How about if we have a different type of scenario where we have, I don't actually have the answer on here, so I'm not 100% sure, but I feel like it's pretty safe. 1.38 divided by 1.09. Yeah, looks about right. So if we have another example, oops, different color. If we have something like solve the future value, which we haven't seen before, so we haven't seen this formula before, but it will become very familiar very soon. Okay, and so it's going to be FV, which is the future value, is the PV with the present value, times 1 plus I to the power of n. Solve it for n, of course, because it's in the power. So how we're going to work this is we're going to have, so we have the future value is the present value times 1 plus I to the power of n. Trying to get n on its own right? We have to divide both sides by the present value. So we get the future value over the present value is 1 plus I to the power of n. Now we can't do anything with 1 plus I to the power of n because we need to take the log of both sides to bring that n down in front. And so we're going to take the log of the future value over the present value, which is going to be the log of 1 plus I to the power of n. Later on, what you'll find is I'll just bring that n down in front right away. So I'm not going to write this step. I'm just going to write this next step. And you can do that as well as if you want future value over. So the log of the future value over the present value is n times the log of 1 plus I. Just because I know that the reason I took the log is to bring that power down in front, so I don't actually have to write that middle step there. Okay. Now I can solve for n by dividing both sides by the log of 1 plus I. So I get the log of the future value over the present value over the log of 1 plus I is n. And what you'll see on your formula sheet later on, I didn't bring a copy, but this formula's on your formula sheet. But it could be a fun question if I asked you to solve for n on test 2, maybe. I don't know. We'll see. I'll give you a warning if I do. Okay. So, any questions about that one? No? How about example 128? Solve 3 plus y to the power of x is 34 for x. So now we have, I'll just rewrite it here, 3 plus y to the power of x is 34. You can come in. Didn't want to. Tell him to come in. No? Too scared? Okay. So, we want to bring that x down in front, right? So we have to take the log of both sides. That's the only way that we can shake out this x. And so we do, and this is where I'm going to start writing down just x times log of 3 plus y, just to skip that middle step. So I get x times the log of 3 plus y is the log of 34. Remember, it's really important that you do take the log of both sides, right? Otherwise, it's not staying equal. So now I can solve for x. X is going to be the log of 34 over the log of 3 plus y. We're actually done here, right? Because we don't know what y is. Right? So I'll make a note here. We can't simplify any further because we don't know no, I almost wrote y as in WHY, but it's just we don't know y, the variable y. We don't know why. But so then we would just end it there. And I think that those are lots of rules to learn in one day. And so I'll post a Moodle quiz on this stuff and we'll start simple interest on Monday. How about? Sound good? See you guys on Monday. It's been a long night already. Oh, is there messages? Yeah.
It's just so distracting. I don't know whose it is, but it's like constant.
If it's the vibrate, maybe turn it off for class. If it's a pling, definitely turn it off for class. Cool. All right. See you guys on Monday. All right. Oh, end this recording. Does anyone need these notes up still? I'll post them on Moodle. Oh. All right.